I'm going to be very quick. We're having a slightly late start. So, without further ado, I would like to welcome Hugo Mulder up to the stage, who's going to introduce Tristram's presentation as his colleague and friend.
Tristram, yeah, there you are. Thanks, Jane. It's a great honor to introduce Tristram. And Tristram, maybe you can come up to stage. Tristram is a structural engineer and sits in the Arup group board. He's also an Arup fellow. And that is a position that is awarded to those in Arup that have contributed to Arup's reputation in terms of innovation and design. Most of you will know the Beijing water cube, the design of which was Tristram's. He was responsible for delivering that design. Yesterday at the talk shop, we spoke about a lot of topics, and there's two things that sort of sprung out for me. First was the idea of people. We here at Smart Geometry are like a great group of people, but it was suggested that instead of smart geometry, we should be talking about smart people. And I think that's what we are, and I think it's an interesting thought. The other one was the idea of collaboration. And that is what Smart Geometry is all about, collaboration, right? We are a gathering of people from all different backgrounds coming together for this event every year, all bring something different to the table and work together in these teams, these fantastic teams that we call clusters. And through those collaborations, some magical things sometimes happen. I think we could see some of the results yesterday at the exhibition and today in the presentations. Arup, and I think Tristram's view will support this, is all about collaboration. So not many great designs have been sort of conceived and developed by a single individual, especially the complexity of building projects. I think just Arup as a place for collaboration, I think that makes Arup such a great place to be. Tristram will explore in his talk through a number of projects which aspects of design can be better addressed using the digital tools and which can maybe be better dealt with using the softer tools such as judgment, intuition, and hunch. So Tristram, over to you.
Thank you, Hugo. So thank you, Jane, thank you, Hugo, for inviting me to come and talk today. I feel a little bit worried that I'm sort of in the wrong place slightly. I'm a humble, practical structural engineer, and I'm interested in projects, and particularly projects that get built. And I feel that I'm slightly out of phase, I think, with the fantastic exploratory work I saw that you've all been doing in your workshops this week. Unfortunately, I didn't attend your talk fest yesterday, but I was very impressed by walking around the exhibition yesterday evening and seeing the work you'd done, you know, in merely 4 days. It's just fantastic. So I'm afraid in some ways, I feel like the person with a hangover, bringing everybody down to earth a bit with a bit of a bump on the day after. What I was proposing to do is just show some projects that I've worked on recently in the last sort of 4 or 5 years and simply tell the stories about why we made the decisions we made or what the basis of the project was, and leave it largely to you to draw conclusions or any conclusions or inferences from those stories. I'll talk a little bit about the digital world between projects and try and produce a vague conclusion at the end, but we'll wait till we get there. So the first project is this funny bridge. This is in the brick pit at Homebush Bay in Sydney. This is the Olympic Park. It was proposed to be the water gateway entrance to the Olympic Park for the Sydney Olympics 2000. But it was discovered just before it was filled with water that living in the bottom of it was a green and gold bell frog, an endangered species in Sydney. Therefore, it couldn't be touched. So what happened is, sort of about 10 years later, the Olympic Park Authority said, well, what are we going to do with this brick pit? And they decided, well, its characteristic was it had green and gold bell frogs. So the answer was to install some kind of viewing platform so that you could go and look at the frogs. Whereupon we get into a sort of an immediate design conundrum that the herpetologist, the frog experts, said, well, you can't go too close to them, you might upset them. Okay? But the problem is, they're this big. Okay? So we designed this platform that's 200 meters in diameter, but it's also 20 meters up in the air so that it doesn't upset the frogs. So you can see it became a little bit of a challenge. What are we actually trying to do? The very least thing we decided that we should try and do is to design something that looked ephemeral, that looked as though it was tiptoeing around the park or around the pit, and that looked as though it was doing what it was meant to do, which is not to disturb the frogs. So we came up with a structural concept which is inherently unstable. In cross-section, it's simply this X, which will fold up about its middle point if it comes under any load. But the geometric trick, of course, is to not just live with a section, but to look at what we can do in 3 dimensions and to rotate it, spin it round a disk, a circle, until you get a 3-dimensional form, which now is stable, but it still maintains or keeps this visual quality of looking as though it's unstable. So it's a sort of visual trick. Now, in this case, this project, all these decisions were made in the judgmental, subjective world. There was no exploratory work done, I don't think, inside a computer. I simply used my own experience to say that this structure would work and then proved it later, which is, if you like, the traditional approach, at least to structural engineering. You conceive it on the back of an envelope, you work it up with the architect, and then when everybody's agreed that's what you want to do, you turn on a machine and prove that it will actually work. And that's exactly the path we followed here. The last piece is we also made a decision to use these, to make the steel pieces out of cruciform elements, cross-section as a cross. These are not the most efficient way of doing it, so any parametric or ambitious trying to optimize the structure would not have concluded that we should use cruciform sections. A circular tube is a far more efficient way of carrying a compression force over a distance. But shadows and light play totally differently on cross-sections, cruciform cross-sections, than they do on circular tubes. And because you're always seeing 2 different faces, whatever way you look at it, one of them is typically darker than the other, and it almost halves the visible size of the element. So again, a decision is made here to use a less effective or less efficient piece of steel, but for a very subjective reason, a reason that we think simply it looks better. And it reinforces the whole idea of tiptoeing around the pond and not disturbing the frogs. By the way, the sort of punchline here is the frogs only live in the brick pit. This endangered species only exists there because it is disturbed ground. In between projects, I'm just going to put up a few things about the digital world, if you like, what my view of the digital world. It started for me from here. I saw some research about 10 years ago that showed that even though the construction industry is about 10% of the GDP of the Western world, it's a similar scale to manufacturing. Various studies have been done, but a lot of them conclude that really in the last 75 years, the productivity in the construction industry has not changed. So in the last 75 years, there's been a huge change in manufacturing. If you think about white goods, cars, anything like that, they're becoming increasingly sophisticated and increasingly cheap. Whereas construction really was still pouring sloppy concrete on site in timber formwork. It really hasn't changed in the same period. And there are lots of reasons for that, which I won't dwell on. So I think we're actually on a bit of a change. We're in a place where there's a whole revolution going to happen across the construction industry across the world, which is just as well because we've got 9 billion people we're going to have to accommodate, of which probably 5 billion are going to be in cities, which means probably building more city between now and 2050 than currently exists. So if we can't do it more effectively than we've done in the past, we're not actually going to have a future. So this goes across the whole aspect of the built environment to me. It starts with sort of planning and virtual design. And again, when I started, buildings were their own prototypes. You didn't really know what you were going to get until you built it. And at the same time, the manufacturing industry made physical prototypes, and they tested them. And after they tested sort of 20 or 30 cars, they went into production. We now actually use the same tools. We all explore things in a virtual world. We can do the crash testing virtually. We don't have to do it physically in the car industry. And we can make sure things fit and operate in a virtual world and make sure we're achieving the conditions we want to achieve before we build buildings. We haven't yet properly taken advantage of that, in my view. But it goes to more than that. We can then manufacture the building because we know what we want before we start. It used to be the builder had to interpret the design drawings really on site to come up with something that worked. You can then manage your buildings or your built environment using the information you've already got and operating it in a way it was intended to be operated. Again, buildings at the moment typically use 50 or 60% more energy than was predicted simply because the occupants don't occupy the building in the way it was predicted or the building managers don't manage it in that way. Smart infrastructure I'll talk a little bit about later and behaviour and feedback. So as I said, virtual design is the bit I think most people in this room are probably interested in, but I just want to put it into its context. So I'm going to talk a bit more about the other things as we go along. But just the virtual design one, I wrote this slide, I don't know, 3 years ago. There are issues about concept models. There's issues about if we go virtual too soon. The problem in the virtual world, it is definite. It knows the difference between a millimetre and a tenth of a millimetre and a centimetre. And the problem is we tend to attack it or use it in this definitive fashion. And if we put together concepts and worry about things being accurate to the nearest millimetre, then we're spending too much energy and time modelling at that stage when we should be thinking. There's the interchange with analysis. At the moment, we move all the data in and out of different software environments. It takes huge effort, huge time, and huge loss of fidelity in the stuff that's moved around. Whereas, we would look forward to the day where the analysis, or the verification, I could call it, is done within the same environment that we're actually designing. It's not that far away, but it's not quite there. A simpler thing, common models. All members of the design team and the client and the contractor using the same modelling environment. Again, huge interaction issues because we're not at the moment. And at a lesser level, even when we're not, moving the information between collaborators because we're not in the same space. And the world has ended up with more specialisations than really it should have. And therefore, the number of members in any given design team has become huge. And therefore, we now have a new specialist, which is the integrator, who works across the top and tries to communicate between them. The second project's also a bridge. In fact, I've got 3 bridges, a couple of stadiums and an office building. And I should have said the first bridge, the brick pit, was with an outfit in Sydney called Durbach Bloch Architects, a relatively small firm. All the other projects I'm showing were a collaboration with Philip Cox, with Cox Architects, all designed in Australia. So this is the Carilpa Bridge in Brisbane. This was brought about by a rather clever government, I thought anyway, because they said, we're going to have a design competition. Right? But they did a couple of twists to the design competition. They asked architects to lead to enter the design competition, but they said, don't design us just a bridge, design us a bridge, the best bridge you can possibly put forward that will cost 60 million Australian dollars. Okay? And then they said, because we know architects tend to be a little bit unreliable with factual matters, bring to the table a builder who will sign away to commit to build it for $60 million. Okay? So actually it was a design-build competition, but cleverly inverted to be made into a design competition, and it worked out, I think, very well. So our team, Cox, Arup and Balderston Hornibrook, we looked at all these different options in front of you, and we said, well, it's a design competition, so we're not going to do the ordinary things, we're going to do something different. But we're going to do something different that is only going to cost $60 million. And we decided, because we've been recently thinking about it, to do this tensegrity bridge, as we called it, on the bottom right-hand side. As a structural engineer, it's quite difficult to do something with tensegrity because it is inherently ineffective. Now, if you look around the history of tensegrity, you can see some sculptures, but that's about it. Because actually just getting a sculpture to hold itself up is pretty difficult. Yeah? So it's a slightly odd concept to try and design a real piece of urban infrastructure with. So again, we cheated. The top diagram is actually our bridge. It's simply a cable-stayed bridge, yeah, using two pillars, 2 pylons in the river. But then we added a set of structure you can see in the middle of this diagram, which is a whole other set of masts and cables. And you could say, well, all you've done is decorated your bridge, and to some extent that's true. But it's not quite true, because we've halved the span of the deck from 24 metres to 12 metres, which reduces its thickness from about 1.5 metres to 900 millimetres. And in modern pedestrian bridges, you have to deal with disabled access. So you get a ramp of about 1 in 20 to get up onto a bridge and get down. And if you save 600 millimetres in the middle, you save 20 times that bridge length at each end. So it's not the direct saving, if you like, in the middle that we get from this extra bit of structure, but it is what we get at the end. The next step was we put the two together at the bottom. You can still probably see a regular pattern. You can see certainly where the cable stays come together. But if we go one step further and start using random numbers and inclining everything so it's not in its usual vertical place, your loss of efficiency if you incline by up to 15 degrees is about 4%, which probably doesn't change one tube from one size to another. So it probably doesn't make any impact at all. And by doing different random patterns on each side of the bridge, which you can see in the bottom of this slide, you get a three-dimensional sort of fuzziness about it. You're now beginning not to see the major pillars compared to the major masts compared to the minor masts. So it's all sort of sleight of hand, if you will, here. The funny bit to me is the only digital bit I did was during the competition. I wrote a spreadsheet that generated random numbers and used it to incline the columns and change their height slightly as well. And once I'd done that, we never changed them. That was it. There was no more digital exploration. It was done once. It worked. And we went ahead and built it. There's another little bit of, there's a bit of pure tensegrity, which is there are horizontal struts that support the canopy to protect the people and also keep the mast stable in the other direction. So there are some, because the idea of tensegrity, for those who are not familiar with the work of either Buckminster Fuller or Kenneth Snelson, depending on who you think invented it, is the idea of compression elements floating in a sea of tension. So the idea is that the struts don't touch each other. And that's what actually makes it very inefficient. What amazes me, by the way, is Buckminster Fuller persuaded the world that tensegrity was the most efficient structure in the planet, and he was going to construct whole worlds in the sky based on it. I still don't understand how the whole world thought he was right. It is quite an amazing confidence trick. He's a brilliant bloke, by the way, don't get me wrong. I just think that particular aspect of what he put forward was amazing. And we had done the same thing to some extent. On our judging panel, working for the government, was a quantity surveyor whose job was to make sure that even the builder wasn't cheating and it really could be built for the money that the government wanted to spend. Now, this quantity surveyor looked at our project and actually decided it was the cheapest submission that was made. But he also decided it didn't stand up. So on his farm over Christmas, luckily the entries went in before Christmas and the judging was made after Christmas, the decision was made. And Christmas in Australia is a big summer holiday. So he went off to his hobby farm over Christmas and he built this model using his own money in his own farm to make sure that he wasn't going to recommend to the government to build a bridge that wouldn't actually work. So it's the first time ever, I think, a QS has gone to such lengths, in a physical world. So there's the bridge that we built. I think it's very successful. I think one of its lovely things is it polarizes opinion. I'm told that people on the River Cat, as they pass underneath it, they either love it or they hate it. They don't come halfway in between. When it opened, it was the 150th anniversary, as it happens, of the first tall ships to arrive in the Brisbane River. And so you can also see, unwitting references between what we constructed and the original tall ships. This is a sort of side point. Almost everything I've been involved with since 2003 has had LED lighting using, infinitely addressable colours and dynamically programmable. And all the pictures we take are stills, and they show it in some beautiful, calm lighting that the architect maybe first envisaged. Of course, anybody now can reprogram the lights and make it look as hideous as they want. And this is common now across a lot of buildings. There's a whole new profession required, which is providing the content, if you like, the artistic content for lighting systems. So manufacturing, and it's a moot point to me. Will we manufacture buildings and assemble them on site? Or will we move the manufacturing capability to the site? The former is where all the action is that I see. We've got people like Unitized Building down in Melbourne putting together apartments complete and fitted out in the workshop. We've got Lang O'Rourke here, mass producing custom made concrete panels and assembling them complete with their services and putting up 40-ton pieces at Leadenhall, for example. The job in the background here is a Rogers designed timber housing where you can decide what house you want and 8 weeks later it is finished. So it's 8 weeks later, you've not only built a house, but you've built a house to the specifications and designs that you decided 8 weeks earlier. You know, this is sort of where we're at. I think we've still got a long way to go, and one of the things that interests me, as I was describing to somebody earlier, is, you know, if you can take, and these are real, so at the moment there's a robotic programmer in Australia producing a sniper target sitting on a Segway base, and lots of these run around and learn from each other as to how to not get shot. Okay, and they go and hide in buildings and so on. So artificial intelligence on a Segway bottom. At the same time, we have robotic painting arms in car factories that do fantastic things. Why can't the two be added together and go on site and put bricks together in a similar way to one of your workshops were doing using cameras to decide where it's going? But why not use a robot rather than a person? I think, I'm not saying one or the other, I'm just saying, you know, both are interesting ways of looking at life, perhaps. Things that are missing, if you like, these are the sort of hiccups to me. You know, supply chain management. What's preventing us all moving forward in our industry is we're terribly fragmented. We have tons of different people working at the design end of it, at the manufacturing end of it, and particularly at the supply or trade end of it, down to individuals who are tradesmen. How do we all move forward together? How do we get the capability to spread through the industry rather than being in pockets? I remember being really frustrated, you know, 10 years ago, we'd give presentations to contractors saying, you know, this is the way we should be doing it. And I remember one major contractor turning to me and saying, well, that's all very well, Tristram, we think it's fantastic. You know, your vision of the future is really cool, but we're not going to lead. You know, why would we do something different? Yeah. And then you extrapolate, that's a big player. That's people with capital, money to invest. How does that then work through small, medium enterprises, which make up the majority of our industry? Third and last bridge is this bridge we built in Singapore, the so-called Helix Bridge. And this is interesting because this is a design process that stuttered, stopped almost, restarted, changed direction. The project was to try and build a bridge, or try and make a pedestrian network around, a pedestrian walkway, around this new harbour, Marina Bay in Singapore. Singaporeans have huge ambition. You know, even with a population of only 5 million, they just keep reclaiming land and building more cities. So all the green stuff there at this time was not built. It now is all built. And you can see on this slide, our idea was to build a bridge. It's the pedestrian bridge I'm talking about here in the top right-hand corner, that was curved. And we decided to make it curved for several reasons. Firstly, just to make, to connect, you know, this loop of pedestrian walkway. Secondly, so that it looks different as you approach it. Your perspective changes, both as you approach it and as you cross it. And then I added that I wanted the structure above the bridge, so you experience it as you cross it, rather than, you know, on some bridges, they're beautiful from afar, but when you're actually on them, you know, when you're participating with them, the structures vanish because it's all underneath you and you can't actually see it. So I came up with this idea of, you know, a bent Wild West wagon, if you will, hoops, structure, cables running from end to end, and that's what we submitted. It was only after we submitted it I sort of woke up one morning and I thought, oh, that's a bit of a bummer. It doesn't actually work. Okay, it doesn't work because tension cables will not go round corners naturally. They wish to straighten up. So it was all right for a straight bridge, but it wouldn't work for a curved bridge. So Philip Cox and I said, well, that's okay. We'll just make it out of a compression tube instead. Similar idea. We'll walk through a tube. You actually get into a structural conundrum when you try and do delicate compression tubes. If you make them a bigger diameter overall so that they're more structurally efficient as a bridge, they become very ineffective at the supports and at mid-span. At the supports they want to squash, and at mid-span they want to elongate. And therefore you have to make the members bigger to stop that happening. Or they also, the compression elements want to buckle. All sorts of things happen. So we added to our bridge 2 layers of cables inside it to keep it stable. So we had an external exoskeleton, we had internal stability cables to keep it round, to keep it circular. And we also made it grow and swell, which we thought was interesting. And we also thought it was a reference to a Malaysian fish trap. We thought it was a good cultural reference for a bridge in Singapore. But I'll never forget the day that we went to visit the 2 ladies, or particularly the one lady in that time, Dr. Koh, who was in charge of the Urban Redevelopment Authority, our client. And we presented this scheme, and she looked at us and paused and said, "Professor Cox, Professor Carfrae, why do you think Singaporeans want to be treated like fish? And if they should be treated like fish, why would they want to be caught in your bridge?" And it was one of those sort of, the scales fell away from both our eyes, and we thought, Unfortunately, she's probably completely correct, because we have also managed to take a path where we've ended up with this overly complicated structure. The idea was to give people a good experience crossing a bridge, but they probably now feel as though they're in a cage, was one mistake. The second mistake is the Singaporeans are not necessarily the best friends of the Malaysians. In fact, the whole purpose of Marina Bay is to have a freshwater reservoir so they're no longer dependent on the Malaysian water supply. So we'd made 2 mistakes. So we said, okay, so how do we start again? What do we like? Where are we? Why have we ended up in this wrong place? And where should we go from here? And we said, we both thought that what we actually liked were these elements of the spiral. The elements that went round the bridge in a spiral pattern were the most interesting. So you can see them here as they twist their way down the side, the face of the bridge. And so we said, okay, we're going to make a bridge out of a spiral. But the only problem was, that a spiral is not a structure. It doesn't work. If you've ever seen a slinky as a kid and stretch it out, it just droops between where you stretch it. So this is where I use the machine as an exploratory vehicle. The question here is now, can you make a spiral into a structure? Or more particularly, if you take 2 spirals, one a clockwise spiral and one an anti-clockwise spiral, and while not making them touch, can you interconnect them in a way that makes them into a structure? And, my head was only sufficient to say, possibly. And it's only when you play with this inside a virtual world that you find out whether it's really a possibility or not. And the good news was I did find after a week or so there was a way of interconnecting them. And also that this double spiral bridge goes around a corner. And what's more, even when we went to the URA and said, we got this brilliant bridge, but it might be a maintenance nightmare, they said, well, how do we stop it being a maintenance nightmare? And we said, well, probably make it out of stainless steel. And they said, how much is that going to cost? And we said, probably another $15 million. They said, okay, because by then they were in love with the idea of a bridge that referenced DNA. Okay? This was now future-looking. This was about Singapore as a high-tech, biotech, looking to the future, having an impact on human life and so on. So in this case, that single idea, reference idea, allowed us to add $15 million to a budget of $45 million. Yeah? And the bridge is now constructed, as you probably all know. There's a slight interesting bit of architecture here, that the bridge has some glass panels. It then has a bit with no panels, and it has some mesh panels, and then it has no panels and glass panels. Now, if you've ever been in Singapore when you've got the monsoon downpour, you might wonder why people want to cross a bridge and go wet, dry, wet, dry, wet, dry, wet, dry from end to end. And again, we have the LED issue, but that's the same as I said on many projects. I realise I'm being a bit slow here. I see there's a clock ticking down, so I'm going to have to accelerate a bit. So I'm not going to talk so much about the theoretical stuff. I'll just say that, it is sort of obvious that if you have a building that operates in a virtual world, it has its real performance characteristics, it has all the equipment it needs to work, and so on, you can also compare that operation to what happens in the real world, and you can pass information from one to the other and tune one against the other and learn from both. You're in a more powerful position with both worlds than you would be. Stadiums. The bird's nest is quite obviously, I think, the most beautiful stadium in the world. But it was optimized with only one end, if you like. It was optimized for its looks. It is not the most efficient structural beast in the world. So the challenge was for me, and Philip Cox, is can you design a stadium that, where you optimize both, where you try and make it efficient and beautiful simultaneously? Is this a possibility? And actually, it wasn't just Philip and I, it was and Jay as well. I see down at the front here, 3 of us. And this becomes a very difficult thing to do because the collaboration has to be very intimate at this stage. The structure is what you see. And what you see is completely defined or constrained by what will work. Because what we were trying to do is make a structure in one dimension out of one layer and use the shaping of that one layer as the item that worked as a structure. So the more conventional way of designing a stadium such as this would have been to use cantilever trusses. And this is a structural diagram showing tension in the top of the truss, compression in the bottom of the truss. Or in 3 dimensions, you end up with multiple trusses. If you do this, you add more structure at the top to support the roofing, and you add more structure at the bottom to keep the elements stable, at which point it probably looks a bit of a mess, so you add a ceiling as well. And you end up with a 9-metre depth or so for this 70-metre cantilever, which is unusable space, if you like. It's where the structure is. Whereas if you spread that structure in 3 dimensions, you've still got a top chord, you've still got a bottom chord. You've got the same structural efficiency. You've only got one surface to clad. You have no additional elements to add for stability. And you don't have to provide a ceiling. And you can occupy the space in the humps, which was part of our brief, was to be able to have a stadium that expanded to 70,000 for the World Cup and down to 50,000 after the World Cup. So this was for Durban, for the Soccer World Cup, and we lost. It didn't get built, okay? But I still haven't given up on the concept, at least, and we'll show you one in a moment that works. This is the next stage, I guess, of the asset thing, is smart infrastructure. This is where the Internet of Things allows you to have an infinite number of sensors and actuators in the built environment being controlled from the Internet. I'll leave it to you, really, to think a bit more about what that potential of that is. But it means we can match up, really, supply and demand in a temporal fashion. We can get things to link together so that our energy is delivered to where it needs to be, when it needs to be. It's not being delivered to the wrong place. And that's really important in the concept of renewables, which tend to be a bit sporadic. So we've got to get better at matching up generation with requirements, if you like. And the same goes for traffic. We at the moment have halved the cost of the Forth Road Bridge simply by saying you can use the existing approach roads by using intelligent transport systems and getting the maximum throughput out of what you've already got, rather than building new and bigger roads. Next project is another stadium, and a real one this time. This is the Amy Park Stadium, or the rectangular pitch stadium in Melbourne. The concept here of using these domes, again, was conceived of in our heads, if you like. It was a structure, it is a structure, it will work. But we went to quite a long length to then optimize it using parameters. So we built a model where the red lines on the left here are the things we control. All the rest of it follows from that. So as you adjust the red lines, you get a new structural form completely through a parametric model. But then we lift that model out every time we adjust it, make a structural model, analyze it, optimize the steel weight, see how efficient it is. We lift it out and look at it. Do we like the look of this shape? Is it a better shape? Is it a worse shape? We lift it out and look at the panelization of the facade. How much repetition are we getting of the triangular panel shape? So this is a 3-element or 3 different dimensions optimization, but it's not automated. And my experience has been I learn more when you don't automate it than when you do. Because the problem with automation is you have to decide, you have to know what you want before you start, if I can put it like that. Whereas when you don't automate it, you learn as you go along and you keep changing your approach, you keep changing your strategy according to what you've learned from the last one, if you see what I mean. So in general, on real projects, I find that more successful. It probably just means I'm of an age or a generation or a mentality where I can't really do proper optimization. I'm not saying it's the answer, I'm just saying that's my experience. This image is the project in the computer. This was the computer-generated image before we built it. And this is the project as built. And so the other thing here is this idea, you know, as I said before, of virtual prototypes. We can determine pretty much what we're going to get before we commit to making it. And this is the building in use. Again, you can see this idea of a single skin, single layer, using the... in this case, it wasn't to extend the stadium up into those arches, but it was to give people individual places to live. It was a bit like the idea of the nooks at the back of a club, you know, the curved benches at the back of a club. You know, I always, you know, we thought a troop of spectators might always go to one hump. You know, that might be where those people always collected for their match. And here you have it. And these images I do find on this project quite odd because they look like CGIs, but they're not. These are the real thing. And it lights itself up at night, which for a sporting precinct like the one in Melbourne is fantastic because the people in the city can actually see it. They know what's happening. They get connected, you know, to their sporting environment, whereas when the sports facilities are banished to the suburbs, it really isn't anything like as good. Behaviour. This is extending the idea of the Internet of Things to the idea that actually we, as people, are both sensors and actuators. And if we're given information, we will change our behaviour and utilise things differently and ultimately utilise things more efficiently. And we'll learn from that. You know, there are all sorts of examples of this. A simple thing. If we really know the state of the public transport system, we would use it slightly differently. We wouldn't all get on the train at the same time or try and wait for the same bus. And the last one is feedback. This is also now being talked about, if you like, as collectively, I think, as big data. The idea that if you actually know what people do and know how they use things, then you can change the way things work to suit how they want to use them. I mean, I think a classic of this is if you do a public square and fill it full of grass, don't decide where the pathways are at the beginning. Leave it with no paths until people make paths by walking across the square, then put the paths where they've walked. You know, that sort of analogy can be applied across the whole of the built environment. This clock is very daunting, by the way. I have 5.5 minutes left and one project, so I think I might get there. This is 111 Eagle Street, which is a new office building, again in Brisbane. It was a very, very difficult site because we were trying to insert a new building between two very beautiful modernist buildings by Harry Seidler. One of them an office building, one of them an apartment building, or mixed use, including a car park at the bottom. And our site was right in between them, as you can see on this plan, where the two grey blocks are the two existing buildings. Not only were we squeezing our new building in between, but it was all sitting above an existing operational basement. And in the centre of our site was the goods loading dock entrance, okay, which you can still see, the ramp there. So if we weren't going to demolish a lot of the existing and rebuild it all at extra cost and delay and in an unsustainable fashion, instead we said, well, how can we make a new building that inserts itself exactly around the parameters of what already exists? And decided, yes, we probably could. So the core is offset, at which point it no longer supports the building properly against wind loads. This is a 45-storey building. And we decided to put the perimeter columns where they most easily could penetrate the 3 levels of existing basement. So rather than disrupting the existing basement and car parking arrangement, we put the columns where they could be. So we then extrapolated that and said, so if we start with a random set of columns, and we know that we want a perimeter frame structurally because the core isn't adequate because it's off-centre, then can we actually grow a set of columns up the building which will work as wind columns and also work as a pattern that interacts properly with this random set of starting points? I'm finding this quite difficult to explain, but basically we wrote ourselves a computer algorithm. We wrote and rewrote and rewrote and rewrote. So we developed a computer algorithm over a period of about a month or so, where we grew a set of columns up the building, but we controlled inside the algorithm this time the structural efficiency of the outcome. So we distilled the idea of structure to a few different parameters. For example, we said the columns need to lean at least 5 degrees at the bottom because the ratio of the gravity load to the wind shear is about 5 degrees, and therefore they will work effectively to support the wind load if they have that amount of angle. we said we want to minimize the spacing of a column at a slab to 8 meters, because the slab will efficiently span that far. We don't want a gap between columns that's bigger than that. Then rather than writing a really complicated way of trying to match these parameters, we simply allowed the program to generate random collections of columns, one level at a time from the bottom upwards. And it just carried on generating a random set of columns until it found one that met the parameters. It then moved to the level above and did it again. And the third parameter, by the way, is that the columns had to be in balance. There had to be as many leaning left as right, and front and back and twist both ways, so that it would actually, under a gravity load, it didn't move. No, it was still vertical. What we found is that we just tightened up the parameters until we could just meet them, And we found that, in 2 million iterations or thereabouts, we ended up with 20 buildings that would work, that we actually grew all the way up and met the parameters from bottom to top. And then we just looked at them again and said, do we like it, do we not like it? And or do we like this set of buildings, have we got the randomness right? And we therefore rewrite the script each time to change it until we got 20 patterns that were of the right flavor, from which we simply chose one, and again, we moved forward, and that's what we built. It was also a wonderful coming together for me because we had generated the structure. There was only one definition of it, and so we managed to pass data between the engineering and the architects seamlessly because there was only one version of the truth, and another version wasn't possible, if you see what I mean. You couldn't just draw one because it had been generated in the first place. This is proof for the engineers in the room that it works. The left-hand side is the gravity load. You can see all the columns are being used appropriately. The right-hand side is the wind load, so we've got simply a transfer across the building to the compression on one face. This is the architectural version of the same thing. They've unwrapped the building and the different colours of the column sizes, so they move nicely from larger ones at the bottom of the building to smaller ones at the top. Larger ones, by the way, being only 600 square, smaller ones 300 square, concrete-filled steel tubes. 2 Revit models side by side. First time we've ever done that, structural and architectural, and again, the information is the same. And now, last year, we finished the building. It was the only high-rise building in Australia that carried on construction through the financial crisis. Almost every other every other high-rise building stopped. This one, which of course is exactly the right thing to do, because when it came onto the market, everybody was desperate for office space because nothing else had been built. We played a lot of games, with the pattern and the glazing to try and make sure we could see the columns both during the day and during the night, but without going to the large expense of representing them in the facade itself. So the facade is absolutely uniform, regular, modular, typical curtain wall, but the columns are still seen through it. So this is my last slide, and I think I'm about 1 minute overdue. I was on a judging panel earlier in the week on Monday for the World Architectural News, looking at their competition to select 21 architectural practices that will have an influence, a profound influence on the architecture of the 21st century, 21 for 21. The criteria being you shouldn't have been in business for more than 10 years before entering this award. There were brilliant projects and brilliant bits of architecture that we looked at. But they tended to be brilliant in one or maybe 2 aspects of architecture, if you will. So I came out of that thinking what I would love to see, I think, is something or somebody or some project that manages to combine the whole lot. Right? So I've set out here what I think has become my ambition, if you like, is to use all the tools and advantages of the digital age, both in terms of virtual design and manufacturing in particular. To use it to make your building as efficient as it can be, to minimize the amount of resource you consume, because in the end we haven't got enough, compared to what we have to do. To be as collaborative as you can. Now this is a tricky one, by the way, because a side issue. I'm seeing a digital divide happening in the world between those who are computer literate and are happy and comfortable in a virtual world, and those who quite honestly do not understand what it is. And unfortunately, the majority of the latter are in leadership positions. And so we're getting a problem which is more complicated, I think, than it even first seems, because the teaching and the handing of knowledge and experience is not crossing this digital divide. So I think there is an educational issue here, not just in educational establishments, but in industry as well. And it's sensitive, so my perfect project would also show sensitivity to context and culture. We see beautiful work being done in India, in Africa, and in remote areas of China, but they don't incorporate the things I've said above it at all. So the digital glove-laying bricks is a perfect example of what I want to see, if you see what I mean, of how to combine technology with culture. That ultimately it's all about improving people's lives, and not just from a functional point of view, of course, but from a spiritual one, the last one. So that's me for today. Thank you.